So, for today's lecture, we will be tackling the volumes of solids of revolution, or the method of rings. There are actually three methods: disk method, washer method, and the shell method. But for this video, we will only tackle the disk method. So, before we begin, let's define some terms. Volume is simply an amount of space that an object occupies. Next, what about a solid of revolution? Well, to get a solid of revolution, let's first start out with a function. Let's take for example y is equal to x squared on an interval 0, 2. Next is to take note of the axis of revolution, basically a line which will help us determine how the given function will revolve about. We then rotate this curve about the given axis, in this case, the x-axis, to get the surface of the solid of revolution. This is basically the shape of the volume we'll be looking for. So, now that we've defined a solid of revolution, we will now try to understand the concept of getting the volume of the given solid using the disk method. First, let us learn the theorem behind the disk method. So, let the function f be continuous on the closed interval ab, and assume that f of x is greater than or equal to 0 for all x in the closed interval ab. If S is a solid of revolution obtained by revolving about the x-axis, the region bounded by the curve y is equal to f of x, the x-axis, and the lines x equals a and x equals b, and v of cubic units is the volume of the solid, then v is equal to the integral from a to b of pi times f of x squared dx. This method basically divides a solid into n pieces of disks. We then approximate the volume of each piece, then take the sum of the volumes, as we also take the limit as n approaches a certain number, depending on what the intervals are. In the function that was drawn, we've taken note of the axis of revolution, which is the x-axis. And if you notice, when you rotate the curve about the x-axis, it fully covers the function within the integral at 0, 2. This means that the axis is a boundary of the curve, which is one of the requirements for the disk method to work. The next step is to draw a rectangular strip, and from this strip we can derive the element of volume, which is simply pi times radius squared times thickness. The radius in the equation is basically the length of the strip measured from the axis of revolution, while the thickness is delta I x. Take note that the strip we've drawn on this function is vertical. This is the case because we want the strip to be perpendicular to the axis of revolution, since this is the second requirement for the disk method to work. Also, since we use a vertical strip on the function and that the thickness is delta Ix, we must also take note that the values we write on the element of volume is all in terms of x. In the case of a horizontal strip, we write the values of the element of volume in terms of y. Now, let's fill out the element of volume for this function. Thickness is delta Ix, and in this case, since it's a vertical strip, radius would be top y value minus bottom y value. In the case of the horizontal strip, radius would be right x value minus left x value. So the y value of the curve in terms of x, since it's delta Ix, would be x squared, while the bottom y would simply be 0 since it's the x-axis, and the x-axis's y value is 0. So, once we've simplified this, we can then integrate between the limits x equals 0 and x equals 2. So that's pi times the integral of x to the 4th dx from 0 to 2. When we integrate that, becomes pi times the integral of x to the 5th over 5 dx, evaluated from 0 to 2. Then, when we substitute, it becomes 32 over 5. And so we end up with 32 pi over 5. So basically, the steps for finding volumes of revolution using the disk method are: 1. Draw the graph of the function and take note of the axis of revolution. 2. Draw a vertical or horizontal strip within the specified boundaries. 3. Set up and fill out the element of volume, which is pi times radius squared times thickness. 4. Find the limits of integration. And 5. Integrate between the limits along the axis perpendicular to the strip. Also, you must always remember the following so that the disk method will work. A. The axis is a boundary. B. The strip is perpendicular to the axis of revolution. C. The element of volume is pi times radius squared times thickness. Now that we know the basics of how to use a disk method, let's do another example. Let's draw the function f of x is equal to x minus 3 squared plus 1, x greater than 0, that revolves around the x-axis and calculate the volume of the resulting figure between the lines x equals 0 and x equals 5. So, let's write down the element of volume, which is pi times radius squared times thickness. Since the axis of revolution is the x-axis, we'll be drawing a vertical strip since we want it perpendicular to the axis. As discussed earlier, the thickness is basically the strip, and since we drew a vertical strip, we would label the thickness as delta Ix, which means that the values we'll input in the element of volume will all be in terms of x. Next, the radius of the disk would simply be square bracket x minus 3 squared plus 1 close square bracket since the top y value minus bottom y, which is x minus 3 squared plus 1 minus 0. So if we integrate between the limits of x equals 0 and x equals 5, we get pi times the integral of x minus 3 squared plus 1 squared dx. So we'll just fully expand the integrand because that would become easier. And so that would become x to the 4th minus 12x cubed plus 56x squared minus 120x plus 100. Then when we integrate, it becomes x to the 5th over 5 minus 3x to the 4th plus 56x cubed over 3 minus 60x squared plus 100x. And when we properly substitute, it then simplifies to 83.35 units cubed. Let's work on another example, but this time let's make the y-axis the axis of revolution. Here we have the function f of x is equal to 1 minus x squared, x greater than 0. This function can actually be written as x is equal to the square root of 1 minus y. Let's draw that out first. Let's calculate the volume of the resulting figure between the lines y equals 0 and y equals 1. Next, let's make our strip. Since the axis is the y-axis, that means we'll be drawing a horizontal strip. Now that we've drawn that, let's fill out the element of volume, and the equation for that is, once again, pi times radius squared times thickness. So thickness is delta Iy, meaning everything will be in terms of y, and so the radius would then become square bracket the square root of 1 minus y minus 0 close square bracket squared, simplifying the whole element of volume into pi times square root of 1 minus y squared dy. So now we can get the volume of the solid. The equation would then be pi times the integral of square root of 1 minus y squared dy from 0 to 1. Since that's raised to a square, the square root is removed. Then, when we integrate, it becomes y minus y squared over 2. Then, when we substitute our values, we get a final answer of pi over 2. So that is the volume of the solid. That's basically it for the disk method. Just remember the three requirements. 1. The axis is a boundary. 2. The strip is perpendicular to the axis. And 3. The element of volume is pi times radius squared times thickness. Also, if it's a vertical strip, we use delta Ix as thickness and all the values for the element of volume is in terms of x. If it's a horizontal strip, we use delta Iy as thickness and the values for the element of volume are all in terms of y. And that concludes our tutorial of volumes of solids of revolution using the disk method. Thank you and hope you learned something new today.